I am Dr. W.B. Gurnale from Kamla Nehru Mahavidyalaya, Nagpur. Today we are going to discuss the chemistry of actinoids. Already we have discussed in last lecture the details about the lanthanoids. Now today we are discussing actinoids, that is the second series of the F block element. And actinoids are the 14 elements, and all these 14 elements have been separately shown at the bottom of the periodic table. So this is the last series, and actually these elements are also known as the inner transition element, and majority of the elements are the man-made elements are here, and therefore these elements are man-made elements are also known as the transuranic elements. And here detailed electronic configuration, after that the oxidation state, atomic and ionic radii, all these properties we are discussing in today's presentation. So the topic is transition and inner transition element, chapter 8, and in this already we have discussed the transition element and also Lanthanoid series element, and here today we are discussing the actinoids, and actinoids different topics are given here. What is actinoids, properties of actinoids, application of actinoids, similarity and difference between lanthanoids and actinoids, electronic configuration, atomic and ionic radii, comparison between these different metals and lanthanoid and transition metals, post lanthanoid element. So all these part we are discussing in today's presentation. So first part is the what is meant by actinoids. So here we can say that the group of 14 element following the atomic number 89, that is actinium in the 7th period of the periodic table, and corresponding to the progressive filling of 5F subshell, are known as the actinoids. So these are the 14 elements start from actinium, are known as the actinoids. Among these only neptunium and plutonium occur in the nature and in minute quantities, while other elements have been man-made as a result of nuclear reaction. These are toxic elements exhibiting biological properties, and this series of 14 elements is called the actinoids, and actinoid are the element along with the lanthanoids constitute the complete F block element. The ending IDE in actinoids is not appropriate because it is more correctly means negative ion, such as oxide or chloride. Actinoid were also named actinone by a group of scientists. However, the ending ONE is used preferably for non-metals such as boron, silicon, etc., whereas all the actinoids are distinctly metallic. IUPAC has now recommended these elements to be called actinoids, NOIDS, with the ending OID rather than known as a actinide or actinone. So in place of actinoids or actinone, now IUPAC suggested the name for these 14 elements as actinoids, and therefore the spelling is given here actinoid. And now after this, as we know, these elements are named man-made or synthetic element. These elements are also known as transuranic element. Transuranic element are elements that have atomic number greater than 92. And as we know, in case of actinoids, here the first series, that is actinoid, involve the filling of 5F orbital and known as the actinoid series. After actinium, it includes element thorium up to lawrencium. The chemistry of actinoids is more complicated due to existence of greater range of oxidation state for these metals. All these metals are radioactive, and therefore their accessibility for laboratory investigation is limited. The elements beyond uranium are all man-made elements and are made up by nuclear chemical methods. And some properties are given here that we are going to see about actinoids. So this is the one picture is shown what is the nature of these metals. So this is promethium, europium, actinium, berkelium, nobelium, mendelium, sebaceum. So different color and their nature shown here about that elements. And now important part here that we are going to see is the oxidation state. As we have seen, what is oxidation state? It is the tendency of an element to lose electrons or to gain electron. When the element have strong tendency to lose electron, in that case it has positive charge. And as we know, actinoids elements are all metals, therefore they have strong tendency to lose one or more electron, and therefore they show different oxidation state, also known as variable oxidation state. So they show positive oxidation state. This figure shows the most common oxidation state shown by the actinoid element. So here these are number 1, 2, 3, 4, 5. This is the oxidation number, and here the elements are given: actinium, thorium, plutonium, paramecium, uranium, neptunium. So remember the names of all the 14 elements of actinoids. And here is having +3 oxidation state. This thorium having +4, promethium having +5, and uranium having +6. And then, so most common oxidation state is shown by this element is +3. So most common is +3. This is the +3 shown by majority of the element of actinoids. So from the figure, the most common oxidation state is the +3, and in addition to that, they also show +5, +6 oxidation state and +4 oxidation state. So all these are the detail about the oxidation state. And in case of oxidation state, also we can from this table we can say that here the important points are: actinoid elements show greater range of oxidation state as compared to the lanthanoid elements. The various oxidation state of these elements are shown, and here from this table figure, the minimum oxidation state is also shown is a +2. So minimum oxidation state is +2. See here, this is the +2 and shown by nobelium, and maximum oxidation state is +7. So it is shown here. This is the +7 and shown by here +6, and also some element also showing +7. And +7 maximum oxidation state is shown by neptunium and plutonium, and uranium showing +6. And after uranium, neptunium and plutonium, here these are after uranium, neptunium and plutonium, these elements show maximum oxidation state +7, and stable oxidation state is shown by the neptunium +7. So minimum is +2, maximum is +7. And in addition to that, some oxidation state are stable, some are unstable. And +2 oxidation state in case of actinoid is very rare, and only the one element is given, nobelium. And americium has an electronic configuration 5f7, and it is similar to europium 2+ in the lanthanoid, but exists only in the solid state. And in this case, +3 oxidation state is most common oxidation state, and this is not always the most stable oxidation state in the actinoids. The first four element thorium, paramecium, uranium, neptunium do not show +3 oxidation state. So first element is shown, they do not show +3 oxidation state. So here see thorium, paramecium, uranium, neptunium, these elements do not show +3 oxidation state. In most as the most stable oxidation state. For example, uranium 3+ is readily oxidized in air as well as in solution. The most stable oxidation state of the element up to uranium is the 1, involving all the valence electron. The most stable oxidation state of thorium, paramecium and uranium are +4, +5, +6. However, neptunium shows oxidation state +7 by involving all its valence electron. It is not most stable state. Therefore, neptunium in +7 oxidation state is highly oxidizing, and most stable state is +5. In addition to that, the element can also show +4 and +5 oxidation state. +4 oxidation state is shown by all the element from thorium to californium. However, paramecium and neptunium shows +4 oxidation state. +5 oxidation state is shown by all the elements from paramecium to americium. However, +5 oxidation state is more stable for paramecium and neptunium. The +6 oxidation state is shown by lower actinides, that is uranium, neptunium, plutonium, americium, in the form of their fluoride. The +6 oxidation state is more commonly found as the dioxo ion, and +7 oxidation state is shown by or we can say known only in the oxocation of neptunium and plutonium when alkaline solutions are oxidized by oxygen. So important here oxidation state is shown in the slide. And next important property of this is the electronic configuration. And actinoid have general electronic configuration here is shown 5f0 to 14, 6d0 to 2, 7s2. So here actinium is the first member, but actually the elements start from thorium up to lawrencium. So these are the 14 elements: thorium, paramecium, uranium, neptunium, plutonium, americium, californium, berkelium, californium, yttrium, fermium, mendelium, nobelium and lawrencium. All these are the 14 elements. Remember the name of all the 14 elements, and atomic number start from 90 to 103. So 89 is the first actinium. After actinium the elements start. These are 14 elements are known as the actinoids. So in ground state this electronic configuration is given here, and here 89, so 87 is here. 87 is the atomic number of radon, so square bracket radon is 87 and 389. So radon in all the case, and then 5 here is the 5 last electron goes to the 5f orbital. So here in this case now only the electron goes to the d, not to the f. Then 5f orbital filled progressively one by one. So see here, and 7s orbital have 2 electrons in all the case, and 6d orbital may have 1 electron or 0 electron, and incoming electron goes to the 5f orbital. So this is the +3 oxidation state of this series element, and atomic ladder and ionic ladder also shown in that case. So from the electronic configuration we can say that from this table of electronic configuration, the 14 elements that follow the actinium in the periodic table are known as actinides or actinon or actinoids. They include the 3 naturally occurring elements. One is thorium, protactinium and uranium, and 11 transuranic elements produced artificially by nuclear reaction. After mercury we follow 6 elements from thallium to radium, in which electrons enter the 6p subshell. Radon has the configuration xenon 6s2, 4f14, 5d10, 6p6. At this stage the 7s and 6d subshell have smaller energy relative to the 5f subshell, and therefore next 2 electrons are added to the 7s subshell, and we get the fraction, we get the francium and radium, which are s block element. We find that 5f and 6d subshell penetrate the 7s orbital significantly, and therefore stabilize the relative to the 7p subshell. The next few electrons enter either of these 2 subshell, that is 5f or 6d, and as soon as it is obvious that filling of electron from actinium onward, the energy of 6d and 5f subshell does not vary significantly, and allocation of exact configuration become difficult. And it is because of this reason that different authors have suggested different electronic configuration for actinides. However, the electronic configuration for actinide set out and shown in this table. So this is the electronic configuration, and again now from this uranium onward there is no doubt that 5f subshell is more stable, and general electronic configuration of these elements are shown here. So this is the general electronic configuration: 5f 0 to 14, 6d 0 to 2, and 7s have 2 electrons. So this is general electron configuration, and all the 14 elements have this configuration after radon. So here this is the electronic configuration, and next property is the again now atomic and ionic ladder. And here atomic and ionic. This is the actinoids 3 plus. So see, higher value, then decrease is there, continuous decrease in case of ion. And this is the actinoid 4 plus. In case also 4 plus, they show decrease. So we can say that the size of atom or ion decreases regularly along the actinoid series, and there is a steady decrease in ionic radii with the increase in atomic number is known as the actinide contraction. We have seen lanthanoid contraction. Similarly, actinide also show actinide contraction. And what is actinide contraction? There is a steady decrease in the size of atom or atomic radii from actinium to the last element lawrencium, and this decrease is known as the actinide contraction. And this contraction is due to the poor shielding effect of phi of electrons. And in case of this atomic ionic radii, this is known as the we can say that what is the actinide contraction. So in other words, also we can say that the size of actinide ion decreases regularly along the actinide series, and this is because with the increasing atomic number, the extra charge on the nucleus is poorly screened by the EF electrons, and this steady decrease in ionic radii with the increase in atomic number is known as actinide contraction. So again I am repeating, what is actinide contraction? The size of actinide ion decreases regularly along the actinide series. This is because with the increase of atomic number, the extra charge on the nucleus is poorly screened by the F electrons, and therefore this decrease in the ionic radii with the increase in atomic number is known as the actinide contraction. And this figure also shows comparison of M, that is metal 3 plus and metal 4 plus here is shown. So, and this table also show about the ionic radii. See, atomic radii decreases. See now here 203 in picometer values are given. So this is slowly decreases. See here, and in this case it is also clearly shows the decrease. So in case of as compared to atomic, ionic radii decreases continuously. So these are the values of the atomic and ionic radii given in the table. So this is about the atomic and ionic radii. As we know, what is atomic radius? It is the distance between the center of nucleus to the outermost shell of electron. In case of atom, it is known as atomic radius. Similarly, ionic radius. And now some properties of these actinoid elements are there. And important properties of these actinoids are, it is similar to the lanthanoids. They appear silvery white in color. These are highly reactive radioactive elements. Except promethium, all other elements are non-radioactive in nature. They experience decrease in atomic and ionic radii from actinium to lawrencium, and this is known as actinide contraction. They generally exhibit plus the oxidation state, that is the common oxidation state. So these are some common properties of these actinoid elements. And there are also some important applications of these actinoids. And first is as we know that it is seen that the half-lives of the natural thorium and uranium isotopes are so long that we get very negligible radiation from these elements. We find them in everyday use. And also another application is that plutonium is used as a fuel for atomic reactor as well as in an atomic bombs. Uranium is used as a nuclear fuel also, and its salts are used in glass industry, textile industry, and also in medicines. Another application is that thorium is used in atomic reactor as a fuel rods and in the treatment of cancer. A mixture of thorium and cerium nitrate in the ratio 99:1 is used for making incandescent gas metals. So these are some applications of these actinoid elements. And there are some similarity and differences between lanthanide and actinide. We have seen lanthanide, so we have seen the actinide. So what are the point of differences? So given in this table, similarity, both these elements or series show plus the oxidation state common. This is similarity. We have seen in both the case common oxidation state is +3. Second point is that in both the series F orbitals are filled gradually. So this is also similarity. Third is ionic radius of the element in both the series decreases with the increase in atomic number. So it is decreases. Ionic radius is continuously decreases with the increase of atomic number. This is another point of similarity. Number 4 is the electronegativity of all the elements in both the series is low and are said to be highly reactive. As the electronegativity is low, they are highly reactive. And next similarity point is the nitrate, perchlorate and sulfate of all the elements are soluble, while the hydroxide, fluorides and carbonates are insoluble. So this is the similarity between lanthanide and actinides. Now what is the difference there? What is the difference between these two series? So first difference is that lanthanide show maximum oxidation state +4. We have seen the table of in case of lanthanide. So maximum is a +4 oxidation state, whereas in case of oxidation state in case of actinide is maximum is +7, shown by plutonium, and +6. So see, variable oxidation state shown. So as we have seen, actinide elements show variable oxidation state as compared to the lanthanide, because lanthanide show common oxidation state +3, and in addition to that some elements show +2 and +4. So this is the point of difference. Lanthanide show +4 oxidation state and maximum, and +7 in case of plutonium in the actinide element. Lanthanide do not show this is another difference. Lanthanide do not form complexes easily, whereas actinide elements have a greater tendency to form complexes and with the ligand such as thioether. What is complex? As we all know, what is a complex? Complex contain two parts, metal ion and the ligand. And in this case, actinide element, because of the variable oxidation state, because formation of complex, three important conditions are there. Number 1 is the metal should have vacant d or F orbital or vacant orbital, and second is ligand should have lone pair, and third is the metal should show variable oxidation state. So as compared to lanthanide, actinide elements show variable oxidation state, and therefore they have a strong tendency to form complexes as compared to the lanthanide. So this is the point of difference. Another point is all the lanthanide are non-radioactive except promethium, but actinide elements are, majority of the elements are radioactive in nature. So in case of lanthanide only promethium non-radioactive except promethium, but actinide elements are radioactive. So majority of the elements of lanthanoids are non-radioactive, whereas actinide elements are radioactive in nature. Another point of difference is lanthanide do not form oxocation, but actinide form oxocations such as UO+, UO+, PUO+, NP, neptunium dioxide plus. So these are the oxocations. Lanthanide do not form this oxocation, but actinide forms oxocation. Examples are given here. Another point is most of the lanthanoids are colorless in nature, whereas actinoids are colored ions. So because of the presence of number of unpaired electron, they are colored ions, actinide, and most of the lanthanoids are colorless. So this is the point of similarity and point of difference between lanthanide and actinide. Another table is there of comparison between pre-transition lanthanoids and the transition metal. And here one by one points are given here. In case of pre-transition metal, essentially monovalent show group N plus oxidation state, whereas lanthanoids show essentially +3 oxidation state, and in addition to that they show +2, +4 for certain configuration. In case of transition metal, show variable oxidation state. Transition element, d block element show variable oxidation state. Lanthanoids show only +3, and some elements show +2 and +4. So here essentially the monovalent, generally they show N plus. So whatever the elements are there. Okay. Another point of here is that comparison periodic trend dominated by effective nuclear charge at noble gas configuration. And in this case, lanthanide contraction of is there, lanthanide 3+, and side charges of Mn plus is a less mark. So this is another comparison point. And third similarity point here, comparison is that similar properties for a given group. So in case of pre-transitioning metals, they have similarity, and therefore here also lanthanoids have some similarity properties, but in case of transition metal, substantial changes in properties can occur, and this is another comparison. And next point is that always hard, these elements hard OXN are the donor, preferably negatively charged. Here always hard oxygen halide are N donors, preferably negatively charged. Similar to that, heavier metals increasingly from iron, copper may show a soft character. Next point is that no ligand field effect, is insignificant ligand field effect, and here substantial ligand field effect. Here there are another point, poor conductor, poor coordination properties, coordination number determined by the size, and here high coordination number, this is CN is coordination number determined by size, and coordination number 6 is typical maximum, many exceptions are there. Flexibility in geometry, also in geometry in lanthanide, and mixed geometries are there because of the ligand field effect. And no magnetism found in this case, and show magnetism, and also transition metal also show magnetism, magnetic behaviors. So this is the table shows comparison between pre-transition lanthanoids and transition metals. And as we know that elements in the periodic table found, and in case of that number of elements are there, and up to Lawrencium elements was there. But now in case of post-actinoid elements, and some elements have been discovered and symbol have been given, and in case of this post-actinoid element, most of the elements are now suggested the symbol, and it is observed that element with atomic number greater than 92 are called transuranic element. From atomic number 93 to 103 are included in actinoid series, and those from atomic number 104 to atomic number 118 are called post-actinoid elements. So atomic number from 104 to 118 are known as the post-actinoid element. The post-actinoid element that are known so far are transition metals. They are included as a post-actinoid because similar to actinoid element, they can also be synthesized in the nuclear reactions. 9 post-actinoid elements have been synthesized, and it is difficult to study their chemistry because due to their short half-lives. Example is here we can give an element having atom number 112 has half-life period of only 2.8 into 10 to the power minus 4 seconds with the half-lives of milliseconds only. A little is known about the chemistry of these elements. Rutherfordium forms a chloride, that is ReFCl4, similar to zirconium and hafnium in the +4 oxidation state. Dubanium resemble to both the group 5 transition elementals, niobium 5 and actinoid protactinium with oxidation state 5. So some of these are elements after atomic number 104. All these elements have been discovered from 104 to 118, and here but there is a difficulty of these elements, that is 9 post-actinoid elements have been synthesized, but difficulty to study their chemistry because of their short half-lives. So up to 118 elements have already been discovered, and symbol is also being given for all that newly synthesized element, that is known as the post-actinoid elements. So here today we have discussed details about the chemistry of actinoids. What is actinoids? What is the position of actinoids? What is the electronic configuration, oxidation state, atomic and ionic radii, and after that also we have seen the post-actinoid and what is the similarity between lanthanoid and actinoids, and the comparison between the different types of metals. So here we have completed this chapter number 8 and inner transition elements.